Hi everyone, this is Dr. Shamp, and this is chapter 14, the concluding chapter from our course, Principles of Scientific Inquiry, Biology and Psychology 2056 at Algoma University. So this final chapter concerns wrapping up the course material and examining it in an overall way. So examining in particular a single experiment in the context of some of the challenges that have set out that have been set out or that have been discussed in the class pertaining to whether science can deliver on its particular promises. So we're going to talk about that today, and we're going to examine it through one particular lens, and that's an example in intuitive physics. So first, here's a summary of those four woes, those four challenges that were set out to science way back at the beginning of our course. All right, first, science can't prove any theory true or false. So this was part of Karl Popper's ideas concerning whether science could prove anything true or should be alone about falsification. If it's about falsification, we can't prove any theory true. And that was related to his concerns about the validity of using inductive reasoning. Second, that observations are theory-laden and that theory is underdetermined by data. This essentially means that we can't use observations to identify the correct theory, and that's because the two are so intertwined. Okay. Successive paradigms are incommensurable, or that we cannot determine that one paradigm of thought in science is better than any other because you can't compare them directly. And four, what makes a belief scientific is simply that it's what scientists say. So this is a critique from the social sciences and beyond, pertaining largely to the potential for humans who are the conductors of science to be subject to individual biases so that prevent science from being able to say anything objective. So it's about science being simply subjective, and therefore it's about just what scientists are saying. Okay. Now, collectively, these can be restated by asking a single question. Does nature significantly constrain theory choice or not? So can we use observations to determine whether a particular theory is likely to be correct? And that's what science is all about. Now, as we've talked about in the class, when you examine these kinds of questions, you have to do so not by taking a controversial example, but by taking any sort of simple example, the best case scenario. So given a simple question, and intuitive physics here is not going to be really a simple question, but the experiment we use as an example will be simple. But taking from the best of these options is the way to determine not whether science does, whether evidence always constrains theory choice perfectly well, but whether it can in fact do so, because that's the question that we need to answer. So if science does, or if it does, then science can be useful. If not, then science is in trouble. Okay. Obviously, our book and our course takes the stance that science is not indeed in trouble, and that science and that evidence can, in fact, constrain our choice of theories and direct us to theories that are true. But our book covers several case studies in chapter 14. We're going to just look at the one of them, which should be sufficient for our purposes here. Okay. This case study is designed to address the question of whether nature constrains theory choice then. An individual, a researcher, McCloskey, in 1982 was interested in how high school students understood different theories of motion under physics. So he started by surveying high school kids about their knowledge of motion, particularly with understanding whether their impressions of the laws of motion were more in line with the theory of inertia or the theory of impetus, which are two historically pervasive theories. Impetus theory is when a mover sets an object in motion, the process imparts an internal force on that object, or impetus, that would act continuously to keep the object moving until that force or that impetus was used up, okay, that energy, that internal sort of force. Inertia theory is that an object will simply continue in its state of rest or in its state of uniform motion in a straight line unless another external force is placed upon it. Okay. So the main question is which is right. I'll get to that in a few minutes, but I want to ask a few questions first. Okay. First of all, it's worth laying out that these two theories are not compatible. They predict different motions or paths under different circumstances, which makes them a particularly good example here, because observations should, at their best, be able to distinguish whether one of the theories is true or the other is true. Interestingly, many people have experience that give them the general idea of motion that most closely aligns with impetus theory. So a test can be devised, a simple test can be devised to examine this. If you imagine a person who's running and holding a ball in their hand, holding it at their waist height to their side, and while they're running, they drop that ball. Okay, what happens? What path will the ball follow when released? We consider the main three possibilities that are under common sense reasoning. HA, or hypothesis A, the ball will fall forward with the runner. That is defined by path A, and I'll show you more specifically in a diagram what that will look like. HB, or path B, the ball will fall straight down to the ground. And HC, the ball will fall backwards, path C. Now, I've avoided other, what I would say are implausible possibilities and hypotheses, such as the ball will fly out sideways or the ball will float up into space. I didn't include those. Collectively, though, these three represent the bulk of reasonable possibilities. So in that sense, they meet our criteria for being collectively exhaustive of the possibilities that are out there. Okay. So the experiment itself does allow for the ball to take any of those other paths, like floating up into space, and we can record that observation if it does happen. And if you do this experiment and it floats off into space, please let me know. I'd love to hear more about it. All right, so, but these are the three predictions that are examined here. Okay, here's an illustration of those. So what we have here is path A, designated for hypothesis A. The ball falls in a forward motion, and the path is somewhat downward parabolic until it lands on the ground further ahead of the point of where it was dropped. Path B, the ball falls straight down, and path C, the ball goes backwards. Okay. Now, when McCloskey surveyed students in high school about which hypotheses they felt was correct, this is what he found. Okay, 45% support for HA, 49% support for HB, and 6%, that should read, hypothesis C, 6% for that one. Okay. So this is the point in the lecture that I would typically take a poll of the class to see how many people supported each of the three respective hypotheses. But I obviously can't do that, but feel free in your head to sort of be honest with yourself about which hypotheses you expect to be true. Okay. Then McCloskey, he could have proceeded directly to an experiment, but he also wanted to dig a bit deeper. He wanted to know whether the students' behavior matched the beliefs that they had stated. So he had students try the experiment, but instead of seeing what happens directly, he asked them to drop a ball whenever they wanted in order to hit a particular top target as they were running. So there were three options in that case. HA, in this case, drop the ball before reaching the target, aligns with the expectation that the ball would move forward, and only 13% of people did that, which is interesting because 45% of people said that they believed the ball would travel forward, but many of those people did not actually behave according to that belief. Okay. HB, drop the ball directly over the target. 80% of students did that. And HC, drop the ball after reaching the target, 7%. All right, so that was, at least that one's close to the 6% that was estimated. So actions didn't necessarily follow from the reported belief. In a way, both the first survey and then this little mini experiment are two ways of assessing the belief of those students, right? So the first case, they're asking to people to express their personal belief, but their behavior might be a more accurate reflection of their true belief. You know, they may not have felt comfortable saying whatever expectation they really had. They may have had reasons for selecting another one. Or the possibility is that belief and action are not aligned, as we discussed, where reason is supposed to hold a double office of regulating both belief and action. For some of these students, that clearly is not the case. So this section is about subjective beliefs, but what about the objective motion related to the ball's path? What does the ball do if you do this experiment? Okay, so the true answer is in fact HA, that the ball will travel forward with the runner. This is what actually happens if you do the experiment. All right, when the ball is dropped, its inertia causes it to continue moving forward horizontally at the same speed of the runner who dropped it. This is because no force is acted to change its horizontal velocity. Now there'll be some wind or air friction or whatever that will eventually slow it down, but marginally, and certainly not before gravity takes precedence over it. As the ball moves forward, it also moves down at a steadily increasing velocity as a result of gravity, which is another force acting on the ball. Okay. The forward and downward motions combine to produce that downward parabolic path that was described in that diagram. Now, most people were wrong about this. Only 13% of students in that experiment acted according to this correct belief. Subjective beliefs and objective facts were not aligned. All right, so that's kind of interesting. What happens when your beliefs are confronted with hard evidence about that your beliefs are wrong? So don't be too upset if you yourself got this wrong. This is the laws of motion were argued about for millennia. Well, for a long time anyway. Aristotle, Occam, Grosseteste, Newton, Galileo, they were all very interested in figuring this out, and they puzzled over it for a long time. So in spite of the fact that impetus theory is no longer taught in school, it remains an intuitive belief among many people. So this contrast between subjective beliefs and objective facts presents some interesting educational challenges, right? So these individuals seem to have a belief that is contrary to fact, right? Given that inertia theory is taught in schools, it apparently doesn't have any, it doesn't convince most students, right? Students are resistant to it, okay? These are intuitive beliefs, and these are hard to modify. We've talked about anchoring of ideas. We've talked about how when an idea takes hold, it's hard to dislodge, even when contrary evidence is given. Okay. Before taking a physics course, only 13% of the students took the correct action in this experiment. After the course, that went up to 73%. So that's a great improvement with one physics course, but that still leaves 27% with the incorrect conceptions of motion, which is fascinating. Those 27% of students were not even swayed by a physics course. We're not even swayed by doing experiments and finding evidence contrary to their regularly held belief. So a different survey found that 93% of high school students, this is another group of, a larger group of students, believed in impetus, or at least believed motion followed impetus theory, and a physics course only reduced that to 80%. Right? So that's an even more stark result. Okay. One of the reasons why this belief is so difficult to disrupt or change is that new experiences are interpreted within an existing paradigm. So students who are thinking about things according to impetus theory and then learn that it doesn't work or that it doesn't fit, interpret those results according to their already held views related to impetus theory, right? So a different way of saying that is, it appears that students often rely on the intuitive impetus theory as a framework for interpreting new course material. As a result, the materials can be misinterpreted and distorted to fit the intuitive preconceptions. Now, some of you may recognize that this is something that Popper talked about. He didn't like that some theories couldn't be proved false, right? That some scientists, or at the time, some supposed scientists, and he points out a few in psychology, early psychology scientists, and said that any result could be interpreted within their the grounds of their theory by sort of fitting it in, and so he didn't like that, and that's an area where Popper was absolutely right. So what both are getting at here is the need for people to yield their opinions or views on the basis of evidence. So better results can be achieved if students are asked to first state their beliefs, and then the differences between their initial beliefs and Newtonian mechanics can be discussed and clarified. So you're talking to them about the differences between their beliefs in a very specific and directed way. That you can also encourage people, the people involved, to make explicit hypotheses, then collect evidence, and the collection of evidence can result in more effective learning. Essentially, students discovering that they're wrong, or in some cases that they're right, and reinforcing that they're right for those students, but breaking the chain, if possible, for students who are wrong. So, in spite of the fact that many people don't understand motion very well, or people that do understand it incorrectly, the facts are clear, and simple experiments can be set up to easily test for support of impetus and inertia theory. And because those experiments are so easy and so replicable, like you can do them very simply. I could get 1,000 people to line up and do this ball dropping experiment. We can be sure of the truth of inertia theory with an incredible level of confidence, right? Virtual certainty is what we've talked about in the class, like a probability that the hypothesis, inertia theory, is true given the evidence of 0.9999 with hundreds of nines following afterwards. Okay. In short, according to our author, the author of our textbook, true knowledge of motion is empirical, testable, public, objective, and certain. So empirical because it's based on empirical observation, testable because we have an easily conducted experiment to gain data for that, public because anybody can do that experiment and anybody can understand the differences between the observations. Objective, again, because everybody can do this. This is not something that scientists can only do, and because everybody can do it, it can be more objective. And people can be certain of its objectivity, and certain based on that probability reasoning that I was just talking about. So true knowledge of motion is important in many spheres, spanning from sports to warfare to animal predation, right? So if you're an athlete, you have to throw a ball, you have to understand, or you may have to throw a ball or shoot a ball, you have to understand motion. Warfare, if you're launching a projectile, you want it to hit its intended target. Animal predation, well, some animals use the laws of motion very carefully to hunt, to take curves at a high speed, or to launch themselves into the air to try to catch some sort of prey. There's a great video here examining foxes doing just that, so launching themselves into the air in a very parabolic motion, in fact, in order to dive into the snow during winter to capture prey that are under the snow, hiding it close to the ground level. Okay. So Kuhn once stated that his eureka moment was when he realized that Aristotle's physics wasn't just bad Newton, instead it was just different. If they're just different, then how is it that a projectile launched by Aristotle's theory would miss its target, whereas one launched by Newton's would hit it? And that's a critical question to ask anybody who is a major proponent of Kuhn's ideas, particularly about paradigms. Clearly, these two theories are not just different, right? If you go back to the four woes in the spirit of this example, we can look at that more clearly. First, science cannot prove any theory true or false. Given the three theories of motion tested in our ball dropping experiment, with a bit of time, we can prove one of the theories correct and the others false. Science can clearly produce objective truth about motion. Observations are theory-laden. Theory is underdetermined by data. Essentially, this criticism says that theory and data are so intertwined that data can't guide theory choice. However, the three theories in our test can be distinguished through observations, clearly constraining or guiding our theory choice. They can tell us, observations tell us which one is supported by evidence, which one happens, right? Which motion is followed. The only way that data can underdetermine theory here is if more theories are included, especially those that ignore the common sense reality check and therefore the presuppositions of science. And most of the presuppositions that we all collectively hold in everyday life. So observations can definitely help us distinguish between theories. Okay. Third one, successive paradigms are incommensurable. Someone who believed in impetus but was exposed to our three hypotheses and then undertook the experiment to find support for inertia has undergone a paradigm shift. Okay. The differences between the three hypotheses are clearly coherent and can be publicly understood and publicly tested. They're not simply different theories. One is supported by data, by empirical testing, while the others are clearly not. So theories or paradigms are commensurable. If you believe the results of this experiment, then you've already accepted this to be true, because those two theories of physics are paradigms. They represent two paradigms in our understanding of motion. And finally, what makes a belief scientific is simply that it's what scientists say. Is the difference between our hypotheses only that physicists say that one of them is right? No. One is supported by observational evidence that anybody can get through simple experimentation. In other words, one hypothesis describes the actual path of the ball while the others do not. Now, that's not to say that humans and scientists can't be subject to bias under some circumstances, but as I've said, we have to examine this question in light of maybe a positive example, an example where it seems obvious that science can do this, because the question isn't whether science is once in a while subjected to bias, it's whether science can proceed without bias under at least good circumstances. And this would be an example where I believe that to be the case. Okay. What makes HA scientific is that support for it is obtained by using the scientific method to obtain evidence of the true path of the ball. The central point of this case study is to show that the truth emerges when theory confront data, right? So when data runs into theory, that's when we learn the truth. Right. And there's a great quote about this, the great tragedy of science, the slaying of a beautiful hypothesis by an ugly fact. This quote by T.H. Huxley is drawing attention to the fact that we can't fall in love with a particular idea. There's a danger in that. We have to be ready to let it go if the data tell us that we need to. If we let data or evidence constrain our theory choice. So, are you convinced then that the scientific method can succeed in the face of the four woes that were described in the course? Do you feel that the arguments presented in our text in our class are good ones? Do you feel or do you believe that moving cars are hazardous to pedestrians, which is basically the litmus test for whether you accept all the presuppositions of science? Another way of asking that is whether you believe that inertia theory is correct. Do you believe that evidence can directly support the truth of a theory? And I'll leave it there with, of course, a rejoinder of sample questions at the end. I hope you've enjoyed the course, and I hope you've enjoyed the material that we've discussed in the course and found it compelling. I will be contacting you about organizing some sort of a Google meeting for members of the course, Hangouts meeting, so that we can students can have the opportunity to ask questions prior to going ahead with the final exam. I will also, I would be happy to receive questions about the lectures I've posted online by email as well, and I'll try to send out any answers as quickly as I can to the broader class list. All right, so with that, I'm going to end here, and I will